Hello, pre-calculus students. Today we're not going to learn any new material. We're just going to take the material we've learned and apply it in word problems. Only in our book, they call it applications and models. That's a fancy phrase for word problems. On the other hand, word problems are a good thing. Think about it. If somebody walks up to you on the street and goes, hey, 3x minus 5 equals 20, what's x? Man, you just need to turn and go the other direction. Nobody ever does that. But your boss might come to you and say, hey, how much did we sell in this case? You know, I know I paid out this much in commission, and here's the commission rates, but how much did we actually sell? You know, your boss just gave you essentially a word problem. So we're going to solve problems like that, only they're going to relate to trigonometry, of course. So let's get started. Checkpoint problem on page 331 of our current textbook says, from the time a small airplane is 100 feet high and 1,600 ground feet from its landing runway, the plane descends in a straight line to the runway. Determine the angle of descent in degrees. So this is the angle of descent. This is the angle of elevation. This is sometimes called the angle of depression. And this is the angle of elevation. And it's 100 feet high and 1,600 ground feet. So the runway's out here. We're 1,600 ground feet from the runway. At what angle is this coming down? Well, we know that, you know, the ground, and we could draw a parallel line up here. This would be a transversal. Two parallel lines cut by a transversal. Alternate interior angles are congruent. I learned that in 10th grade, folks. That would be 1980-81. Eek. So that means that this angle and this angle are the same. So if we know this angle, we know this one. Well, this is going to be a right triangle. How do these two sides relate to this angle? It's the tangent function. The tangent of theta is 100 over 1,600. So theta is the arctangent of that, or 3.58 degrees. So this is coming down at a smooth angle of 3.58 degrees. It's going to take you 1,600 feet to drop 100 feet. Obviously not drawn to scale. All right, there is something we need to learn, and that is the difference between frequency and period of a function. So period is how long it takes to go through one cycle. So in this case, here's a sine curve, and let's say it takes 2 seconds to go through one cycle. Then the period is 2 seconds. And you can see I've drawn that here. Now the frequency is how many cycles per time period. So if I have this sine curve, this sine curve, this sine curve, and that's all in 1 second, then I've done 3 cycles in 1 second. Cycles don't have units. You'll notice over here, 2 seconds per cycle, that's just 2 seconds is the period. Cycles don't have units. Here I have 3 cycles per second, so that's like 3 inverse seconds. And that's what a hertz is, and you've heard of hertz. You know, your AM radio operates in the kilohertz range, and your FM radio operates in the megahertz range. That's telling you how many cycles per second, how many sine waves are going through the air per second. So when you see seconds in the denominator, you know we're dealing with frequency. Seconds in the numerator is period. Don't memorize that, just understand that a period is how long. A period is a time period, like 2 seconds. Frequency is cycles per second, or at least cycles per time period. So you can tell that period and frequency are reciprocals of each other, because the period of this function would be 1/3 of a second. Because there are 3 cycles per second, the period must be 1/3 of a second per cycle. So frequency and period are just reciprocals of each other. What you have to do is tell, all right, am I looking for a time period where time is going to be in the numerator, or am I looking for something else? And is time going to be in the denominator, which is frequency? You'll notice frequency, how many cycles per second? There are 3. What is the frequency of cycles, or the frequency of the periods? Now we are going to do we're going to do my favorite problem, favorite type of problem, and that is the buoy problem. Maybe you want to listen to my explanation before you copy all this down. Maybe you want to copy it all down first and then listen to my explanation. Don't try to do both at the same time. So here's our generic function for a sinusoidal. A times the function, that's either sine or cosine, of bx minus c plus d. Now, is it bx plus c? You know, it depends on what book you use. So we're going to do it a little bit differently. Remember, we're going to factor the b out if we need to. And you'll see in this problem we don't. So here in a buoy's kind of chained to the bottom of the ocean. And as the waves go by, the buoy's just going up and down. You know, and so if you were measuring that over time, buoy's going up, then it's going down, it's going up, then it's going down. That would be a sine or a cosine curve. So let's look at some information. I'm giving you this information that's in black. I'm saying the max height of the buoy above the bottom of the ocean there is 10 feet. The minimum height is 6 feet. So up here it's at 10. Down when this wave moves on and it's in the trough, it's at 6 feet. And I'm telling you, there are 12 waves per minute. So 2, 3, 4 per minute. Notice that the time is in the denominator. So is that frequency or period? Think about that. Okay. And then the buoy is in a trough at t equals 0. In other words, the buoy is at its minimum height at t equals 0. All 4 of these things tell us something. So we can average these 2 numbers and we get a midline of 8. So that's my d value, is 8. I also know that my amplitude is 2. How do I know that? Well, the distance from 8 to 10 and from 8 to 6 is 2. So I now know the absolute value of A, and I know D. All I need now is B and C. 12 waves per minute. 12 waves per minute. All right, that's a frequency. So that tells me that the reciprocal is the period of 1/12 of a minute, or 5 seconds. We're going to solve this problem in both minutes and seconds. Not hard. So the period is either 1/12 of a minute or 5 seconds. Well, remember that the period is 2 pi over b. So I can set 2 pi over b equal to 1/12. And so b is equal to 24 pi if t is measured in minutes, or 2 pi over b equals 5. B is 2 pi over 5 if t is measured in seconds. So now I've got A, or I've got the absolute value of A. I've got D, and I've got B measured in either minutes or seconds. And then I'm told that the buoy is in a trough at t equals 0. Well, that's wonderful, because that tells me that it's a negative cosine function. Cosine, remember, at 0 starts at its maximum. You flip that over the x-axis, cosine, negative cosine then, must be at a minimum at t equals 0. So if it's a negative cosine function, there is no c value. There's no translation. So that negative cosine tells me that my A is actually negative. 2. So if we're measuring t in minutes, what's the height of the buoy after t minutes? Then it's y equals -2. So that's my negative amplitude times the cosine of 24t plus 8. Or you can do 2 pi over 5t plus 8 if t is in seconds. Why t? Why did I cross x out and make it t? Well, because our variable here is time, not, x is usually something different, often a length or a distance or something. We're going to, if our variable is time, whether it be minutes or seconds, let's use t as a variable, just to kind of help us keep things straight. So that's a buoy problem. And yes, I can show you how to solve those if there's a translation. But right now, we know that if at t equals 0, think of a sine and a cosine curve at t equals 0. If t equals 0, at t equals 0, if your buoy is at the midline and increasing, what kind of function is that? Midline and increasing at t equals 0 would be a sine curve, positive sign. If it's at the midline and decreasing, well, that would be a negative sign. What if it's at a maximum at t equals 0? That would be a positive cosine, and we just did, it was at a minimum at t equals 0, so that was a negative cosine. If it was anywhere else, there would be a phase shift. So here's the seesaw. We want to measure the height of your gluteus muscle. That's your rear end if you don't know that. As a measure of time as you're going up and down on the seesaw. So you're told that the minimum height of your gluteus is 6 inches above the ground. There's a little piece of wood under there. So your rear end is 6 inches above the ground when the seesaw is down. And the maximum height of the seesaw is when the seesaw is at its maximum, your rear end is at 24 inches above the ground. So we can stop right there. Just not even worry about the rest of this. What do we know? Well, we can average these two values and get the midline as 15. That is my D value. And 15 to 6 is 9 inches. 15 to 24 is 9 inches. So my amplitude, or the absolute value of A, is 9. So we've already got absolute value of A, and we've got D. What's the next bit of information we're told? One cycle takes 4 seconds. 4 seconds is a time period. That tells me the period is 4. So 2 pi over B equals 4. B equals 2 pi over 4 or pi over 2. So I now have my B value. And then I tell you, you're up here at time t equals 0. Well, if you're at a maximum at t equals 0, that is a positive cosine function with no phase shift. So we know that our amplitude is 9, so that A is positive 9 times the cosine of pi over 2t, and then there's minus 0, so we don't have to worry about that, plus 15. So here's a function that models the height of your rear end above the ground on the seesaw at any time t, subject to these constraints that I've written in black. And now you may not know this, but I'm really big fan of Star Trek. In fact, right now I'm wearing Star Trek socks. It's true. And for Christmas, I got 4, Christmas of 2020, depending on when you're watching this, that's when I got them. 4 Star Trek t-shirts and a captain's shirt. So that must have been the year the family decided, we don't know what else to get him. Let's get him Star Trek stuff. And I'm very happy with that. So let's look at a Star Trek example. Back in the original Star Trek series in the late 60s, they didn't have a lot of money as special effects, and there weren't a lot of computers to do special effects. So a lot of times special effects were just flashing lights. So let's say that the light flashes 3 times per second. Well, that is a frequency, because it's not a time. 3 times per second is not a time period. That's a frequency. So the period must be 1/3 of a second. So B is 6 pi. The brightness of that light ranged from a minimum of 10 candle power to a maximum of 100 candle power. So average those, that tells you your midline is 55. And from 55 to 100 and 55 to 10, your amplitude is 45. So your absolute value of A is 45. And at T equals 0, you're at 55 candle power, so you're at the midline and decreasing. That is a negative sign function. Now, if you're still not sure what that means, please be sure to ask me about that in class. How do I get from this information to a negative sign? Ask about it in class. Alrighty, so I now have all the information I need. Again, this is not phase shifted because everything matches up perfectly. So it's negative, amplitude, it's a sine function. My B, there's my variable T, here's my midline. So when sine is -1, I'm at a maximum. When sine is at +1, 55 plus -45 times 1, I'm at 10. I'm at, there it is, the minimum. So I can use this function to say, what is the brightness of the flashing light so many seconds after we start? And it turns out this function will tell us the brightness in candle power. So that's just a couple of examples to show you how we can get our variables A, B, C, and D out of the word problem. And then we have to figure out which function do we want to use based on what information is given to us. Are we going to use a positive sign, a negative sign, a positive cosine, or a negative cosine? And do we need to phase shift that? So we'll talk in class about phase shift. Be sure to ask about that. Other than that, we're done with this video. Have a great day.